From Imperial College London, welcome to this special lecture vodcast.
Good evening, ladies and gentlemen, and welcome to the 18th Schrödinger lecture. I'd particularly like to welcome our friends from the National Physics Laboratory, the Taylor and Francis Group, and Hewlett-Packard, who are generously supporting the lecture this evening. Without the support of these people, arranging such a very large-scale event would be impossible. So thank you very much to our sponsors that make this a very enjoyable occasion. I'm sure that most of you know that the Schrödinger lecture arose from the centenary conference celebrating Erwin Schrödinger's birth, which was held here at Imperial College in 1987. One of the greatest scientists of the 20th century, Schrödinger was best known, of course, for his discovery of wave mechanics, which won him the Nobel Prize for Physics in 1933. This year's Schrödinger lecturer needs little introduction from me. A professor of quantum optics, Professor Sir Peter Knight, has recently taken on the new role of principal of the Faculty of Natural Sciences here at Imperial. Peter first came to Imperial in 1979 after working in the United States at Stanford and Rochester universities and in the UK at Sussex and Royal Holloway. He became head of the Department of Physics here in 2001 and acted as principal of the Faculty of Physical Sciences in 2004 until May this last year. Peter's work has focused in particular on quantum optics and strong field physics, an area largely shaped by the properties of laser light. His other main interest is in understanding how information can be stored, transmitted and processed in different ways using quantum physics as part of a large program at Imperial on quantum computing and information processing. Until December 2005, Peter was the chief scientific advisor at the National Physical Laboratory, although even though he gave up at the end of December 2005, he's still acting as caretaker until someone else can be appointed to take his place. Peter is a fellow of the Institute of Physics, a fellow of the Royal Society, and editor of the Journal of Modern Optics and Contemporary Physics. He's received many awards, including the Humboldt Research Award in 2000, the Thomas Young Medal from the Institute of Physics in 1999, and the Einstein Medal for Laser Science in 1996. In 2004, Peter became the first president of the Optical Society of America, and that was the first time that a president had been elected to that society outside North America, a sign of Peter's international reputation. Indeed, according to those who track scientific performance, he is the most cited atomic, molecular, and optical theorist in the world. Peter received his knighthood in 2005 in the Queen's Birthdays Honours List in recognition for his role in establishing the UK as a world centre for research in quantum optics. It's a great pleasure to have Peter give this evening's lecture, and the title is there, Quantum Entanglement, Weird but Useful. So, Peter, it's up to you. Thanks very much.
Thank you, Richard, for those kind words. He did say to me at the management board last week, "You're not going to have that cat again, are you?" And we will. Okay. I think it's always a useful thing to do in a broad audience to start with a literary quote. I looked around for literary quotes, and as always, students come up with them much better than I can. So here's a quote. Is it local trouble? This is dialogue. Is it local trouble? Let's just say we'd like to avoid any imperial entanglements. and that's for Star Wars 4. It goes downhill from here. So, Schrödinger was one of the major figures of quantum physics of last century. He was born 1887 in Vienna. I discovered that his great-grandmother was actually born here in Kensington in 1816, which is a nice local link that I hadn't realized before. And 80 years ago, in 1926, this tremendous work that the rector just referred to of the discovery of wave mechanics really transformed physics. More than that, he was interested very much in the way that one could interpret this new theory. He was always interested in the philosophy behind physics and the interpretational issues and foundational issues, especially the nature of these funny quantum superpositions, this wretched cat that I just referred to, and the entanglement. They continue to worry us even now, but they are the core of what we use in quantum information processing, as I'm hoping to show you. But we're still worried by these foundational things. And there's a curious comment at the bottom I'm going to refer back to. We now know how we can raise... Now I have to look after natural sciences these days, so I've got to find a way of getting some sort of life sciences into it. We now know how to raise ichthyosauria, I can't even say it, in the zoo. I'll explain in a moment what that means. Right, quantum mechanics. Why was it really so much of a dramatic departure? Well, it really transformed entirely our view of the natural world. It undermined materialism, an idea that had really prevailed since at least Newton. It showed there's no isolated parts of the world, no boundaries. This whole idea of entanglement tells us that the world is a whole. It's got an interconnectivity that no one had really suspected before. And quantum physics really does contradict basic ideas of strict determinism and of predictability. And one thing it did do, at least for many of us in quantum physics, is that it restored human observers to a central role in science, the idea of measurement and of observation. There are deviants out there who believe the opposite, and I can see 4 or 5 of them in the audience. Okay, so where did this idea of entanglement come from? And Arthur Eckert's group in Cambridge have a little sort of amusement project trying to work out the origin of this whole business of entanglement or Verschränken. In 1935, when Schrödinger was actually working in the UK, when he was in Oxford, published a paper in the Proceedings of the Cambridge Philosophical Society, and where you can read what it says here, and it really does summarize this whole business of what quantum mechanical entanglement really implies. Here, when two systems of which we know the states by their respective representatives enter into temporary physical interaction, bring them together, separate them. After a time of mutual influence, the systems separate again. They can no longer be described in the same way as before, viz. By endowing each of them with a representative of its own. I would not call that one, but rather the characteristics trait of quantum mechanics. Now, what he's really saying there is an underpinning. In the same year that this was published was the famous Einstein-Podolsky-Rosen paper, which really questioned the idea of what we understood by physical reality. A really fundamental advance. Okay.
Now, when I first heard about Schrödinger's theory, I did not like it. The reason was I was perfectly happy with the Heisenberg theory.
I don't know if you heard that. That was Paul Dirac, who had been working on Heisenberg representation of quantum mechanics through matrices. And when he learnt about the Schrödinger work, this was a completely different way of viewing quantum mechanics. And as you could tell from the little clip there from Dirac, he was perfectly happy with matrix mechanics, and this business puzzled him. And here's the famous Solvay conference. These very solemn gentleman and lady, I think that's right, lady, Madame Curie just there, who convened in 1927 to actually demonstrate and come to some sort of understanding of quantum mechanics. And we've always used this image of the Solvay meeting, but not very long ago, literally a few weeks ago, well, a few months now, a home movie was found that was made by Irving Langmuir of the Solvay meeting, and I thought it'd be fun to actually show it. So here we go, for that meeting in 1927.
The film opens with quick shots of Erwin Schrödinger and Niels Bohr. Auguste Picard of the University of Brussels follows, and then the camera refocuses on Schrödinger and Bohr. Erwin Schrödinger and Niels Bohr followed by Picard. Schrödinger, who developed wave mechanics, never agreed with Bohr in quantum mechanics, nor with Werner Heisenberg's uncertainty principle. Solvay gave Heisenberg an opportunity to discuss his new theory. Here's French physicist Léon Brillouin, Hendrik Kramers, Bohr's former assistant, and Paul Dirac talking with Max Born, whose statistical interpretation of the wave function ended determinism in the atomic world. These men, Bohr, Heisenberg, Kramers, Dirac, and Born, together with Wolfgang Pauli, represent the founding fathers of quantum mechanics. On the other hand is Louis de Broglie, who wrote his dissertation on the wave nature of matter, which Schrödinger used as the basis for wave mechanics. The owner of the camera, Irving Langmuir, is seen chatting briefly with Bohr. At Solvay, Bohr refined his thoughts on complementarity and sparred with Einstein over the implications. Here he's with Paul Ehrenfest. Kramers' work in Copenhagen on dispersion theory was essential to the development of quantum mechanics. Langmuir, an American chemist at the GE lab in Schenectady, hence the camera, had recently broken his leg and appears to explain to Ehrenfest how he gets around. By 1927, Dirac in the middle had independently developed quantum mechanics and made other significant contributions, as had Wolfgang Pauli, who formulated the exclusion principle. A lively Madame Curie, Born and Pauli working out a problem. Note the changed demeanor as the participants exit from the meeting, except for the smiling William Lawrence Bragg and Peter Debye, Arthur Holly Compton, Owen Richardson, Max Born, Madame Curie, Hendrik Kramers, H.A. Lawrence, Paul Langevin, Albert Einstein, whose famous response to Born and the statistical interpretation of the wave function was, "God does not play dice."
Okay, so there you see quantum mechanics and its interpretation in the making. In that clip, that day was the very beginnings of the dialogue about what it meant about doing quantum mechanics. The whole business of whether God played dice, of the statistical interpretation, that was very much to the core of what they were doing at that point. Okay, so why were they looking so grim when they left compared with when they started? The idea was that they started to work out how to interpret this wave function of Schrödinger's. And in particular, there was this real worry about this randomness that was being introduced as an inherent part of quantum physics. So here's an Einstein letter to Max Born. I find the idea quite intolerable that an electron exposed to radiation should choose of its own free will, not only its momentum to jump off, there's something wrong with the grammar there, but also its direction. In that case, I would rather be a cobbler or even an employee in a gaming house than a physicist. Rather stern. All right, no, we don't want to go there. We want to go there. Here's another. Now I'm going to get my ichthyosauri business a bit straight. What Schrödinger said in British Journal for the Philosophy of Science in August 1952, entitled "Are There Quantum Jumps?" he said this. He said, "We never experiment with just one electron or atom or small molecule. In thought experiments, these Gedanken experiments, we sometimes assume we do. This invariably entails ridiculous consequences. In the first place, it's fair to say that we're not experimenting with single particles any more than we can raise ichthyosauri in the zoo." Well, in my game, we're in the business of raising ichthyosauri. It's what we do all the time. It's this whole business of what we mean by quantum jumps. Quantum jumps, looking at these funny things that Bohr objected to, form the basis by which we analyze laser-cooled trapped ions. So, for example, in Richard Thompson's lab downstairs, in the basement of Blackett, or in Patrick Gill's group at the National Physics Laboratory. And these things could well form the basis of the next atomic clocks. Right, so just to show you quantum jumps, this is rather an old picture now from Richard Thompson of a single mercury ion held at rest, or nearly at rest, and it's jumping between a state that fluoresces, so lots and lots of photocounts, and gets turned off. And what you're looking there is you're seeing this atomic lighthouse of it flashing on and off statistically in the way that Einstein objected to. But it really is true, and this telegraph signal is the basis by which we examine single systems. So we can see quantum jumps, but what about these funny quantum superpositions? How can we make a superposition, these funny businesses by which we can take two particular states, two outcomes, here and here? And in quantum mechanics, you could be here or here when you measure it, but you can also prepare them in a superposition of these things, which is one of the most remarkable things. So how would you do that? Well, in quantum optics, we do this in a fairly straightforward way. What we can do is we took a two-level system, we can apply resonance techniques, either magnetic resonance or laser excitation techniques, by which we got this spinning system, and by bringing in a pulse of radiation, we can turn it into a superposition of up there and down there. Okay, and the little movie here, which Bill Monroe from HP did for us, demonstrates that. And these lovely superpositions can be manipulated. They're the whole basis of magnetic resonance imaging, for example, but they're fragile. When they interact with the outside world, information is spread out into those parts of the world of which you have no control. And because you've got no control, you really can't access those things. So you need to be able to isolate them. Then you need to get in and address them, which is a contrary thing. Okay. So here's the cat. Funny superpositions. This devilish experiment by which you have this box in which if an atom is in one state, I did that rather quicker than I wanted. If an atom's in one state, you could imagine the cat would be alive, it's in the other state, the cat's dead. And I found this lovely cartoon of a whole load of completely spaced out dead cats, and the cops are saying, notice all the computations, theoretical scribblings, and lab equipment. Norm, curiosity killed these cats. And that's absolutely right. If you make a measurement, if you closely observe a superposition, you reduce it to one or other of its component parts. Right. So they're funny things. We can have good fun with them. We can have a laugh about them. But we could use them as well. And I've pinched from Scientific American, jobs for quantum cats. Okay, and over here, quantum chemistry. Over there, quantum key distribution, quantum cryptography, which I'm going to talk about. Quantum chemistry is this business of coherent control, by which you can make alternative pathways for a chemical reaction, quantum mechanical amplitudes for chemical reactions, and they can be tuned and modified by external influence, for example, with a light field. And that means you can tune the outcome of a chemical reaction coherently by using these interferences. And this is the whole business of quantum control, which, for example, John Marangus's group here at Imperial College has been doing some fantastically exciting work in steering things by quantum interference. Quantum key distribution is this business by which we can give you, trust us, we're scientists, we can give you complete security in transmission. Okay, and I'll come on to that in a moment. Right, so two-state systems are really weird. Two-state systems, sometimes you could describe them as a thing called spinners. And spinners are very strange objects. They rotate in a funny way. If you rotate a spin, a half system, a two-state system, by 360 degrees, you don't get to where you started. Okay? So it's time for the Balinese plate dance. So I'm looking for I think 3 volunteers would do. Right? Arta's clearly one. You've got to stand up, the audience can't see you. Tim, you're another. Oh, go on. Right, Balinese, I used to do this with 200 quantum mechanics students in a Blackett lab. You want to be able to demonstrate that you can want to rotate something by 360 degrees and not get back to where you started. If there are some mathematicians in the audience, they can tell their neighbours, later on what fiber bundles mean. Right, so rotate, 360 degrees. 2 lots. I'm back where I started. You can cheat too. So do it again. 360 degrees. Because of the connectivity, you have to go back again. Now, Dirac used to do something like this with the belt of his trousers in Cambridge, and would take his belt off, and the audience was always packed, because that might be the day the Nobel Prize winner's trousers fell down. I thought plates were a better way of doing it. Right, so they are weird, these funny superpositions. And by the way, that business of the minus sign, so you have to go right round again, is actually useful in quantum information processing. It's something that allows us to play around with quantum gates. Okay, so quantum gates, quantum registers. If I take a classical register made of bits, bits can be in state 0 or in state 1. So a 3-bit register could be in states from 000 up to 111. There are 8 of them altogether. Okay, what about quantum mechanics? Well, clearly I can have a 2-state system represented by state 0 or state 1. But I can also put it into a superposition of these things. Okay, so I've stolen this funny little superposition of 0 and 1 from Arta's website. Hope you don't mind. Now, if I take that classical register and now think about it quantum mechanically, I will try and put it into a superposition. I can put the entire register in a superposition of the 8 possibilities, from 000 up to 111. Okay, why is that important? To put a single bit into superposition takes 1 operation. Okay. So in a 3-bit register, I can't put 3 fingers up at the moment, but if you have a 3-bit register, with 3 operations, you could generate 8 states. For an n-bit register, there are 2 to the n accessible states. Now, that means that if I had a 1400-bit register, which is very modest by any computational standard, I've got 2 to the 1400 states. And that's larger than the number of particles in the visible universe. So a 1400-bit register under complete control could outrun the largest possible classical machine. Okay, so what could we do? Well, we're going to need something like this fairly soon. There's lots of different laws called Moore's law. Here is the number of instructions per second for various things as a function of date. And elderly folks like me will know some of the names down here. There are IBM machines down here. There's an Apple II over there, which I used to play with once upon a time. A machine that I did play with very early days, a Cray 1, which we were all fantastically pleased by, was over there. It's kind of depressing to see a PlayStation up there, by the way. Look at some life. Again, I have to worry about life sciences, so there's a bacteria, there's a worm, there's a guppy, so PlayStations are outrunning guppies, but it ain't going to take long before it gets as good as me. Or will it? No, it won't, because this is going to flatten out, because our ability to keep going up that curve is going to run out of steam. And it's going to run out of steam because the number of electrons involved in a gate interval, turning on a gate, turning off a gate, number of electrons involved is halving every 18 months, and we're going to get fairly soon, about 2012, 2013, to a situation where there's 1 electron per gate. And you can't do better classically. So we need to involve quantum mechanics, and quantum mechanics will help. Why do they help? And why do we get extraordinary people in sort of grey belted raincoats sitting at the backs of our talks sometimes? Because of security implications. One of the things that we know is that there are problems that classically are incredibly hard. And there are other problems that are dead easy. A dead easy problem is multiplying. Multiplying numbers just grows polynomially with the size of the thing. But things that are really hard are like factoring. If I give you a big number and say find the factors, it's hard work. It exponentially consumes resources. And a great deal of what we do in terms of encryption is based on that. Okay, and in 1995, Peter Shaw proposed this factoring algorithm, which actually completely transformed the way that this complexity business, or the degree of hardness of a problem, is viewed. If I take these big numbers and say, right, find the factors, the scale of the problem gets worse and worse and worse exponentially with the size of the numbers. So, you know, if I take a 400, well, let's take a 500 integer number, it's going to take roughly the age of the universe to factor using the best classical algorithm and a fantastically fast clock speed classical machine. So a 300-digit number on a terahertz computer would take 150,000 years to find the factors using the best algorithm. It takes 10 to the 24 steps. What Peter Shaw showed is that by using this funny superpositions business and entanglement in the register, instead of 10 to the 24 steps, it comes down to 10 to the 10 for that particular number. And if, now, you've got to work out these ifs now. If you convert a quantum computer under complete control, it's going to require a lot of bits, and it has the same clock speed, there's another if, it factors in less than a second. And there are lots of things which require a security cover time, which is much longer than that. Now, at the moment, we're miles away from these things. The technology is awfully long way away, you know, it should demonstrate it. But there are things with a cover time you want to keep secure for longer than, say, 40 or 50 years. So now you've got to take a punt on things. You've got to make a bet as to whether scientists somewhere out there will develop a quantum computer in a 40-year timescale, because people are recording encrypted data now in the hope that one day they'll crack it. Okay, so that's the background as to why we get funny people funding us. So what we've got to do is to find algorithms to do this and so on. And we've got to build these registers of things under complete control. And at the moment, we haven't got that many bits under complete control. What we'd like to do is to have a great long string of atoms or ions. There are ions there in that picture. That's a single ion. There's a single atom. There's another one glowing under a laser irradiation. Or the alternative is to take strings of neutrals, and there's a program in Imperial College called an atom chip program that Ed Hines, who's sitting over there, leads, where one day we want to be able to demonstrate that you can make strings of neutral atoms under control to make one of these registers. But it's very distant. It's a long-range program. So, as I said a few moments ago, trust us, we're scientists. If there are these rogue elements of quantum physics that are going to be able to make a quantum computer to crack these things, and by the way, there are lots of good applications as well that I haven't mentioned, quantum physics can also restore the status quo and give you back security. And so let's look at the way that you can get secure codes. Ciphers have been known for a long time, going right back to antiquity, but if you look at the origin of one-time pads, these things long beloved of spies and James Bond, it came about 1918 from Vernam and Mauborgne, who worked for the Army Signal Corps in the United States. And what they do is that they have a plain text. That's just your message. First thing you do is you write your message in some sort of binary. That's the best thing to do. And then what you do is you scramble it with a key. Okay, you do modulo arithmetic or something to add a random string of ones and zeros, and that's a scrambled cryptogram. And the recipient is the only other person that shares that key. Okay, so without that key, you can't do the unscrambling. And what Shannon did, there's Shannon, in the 1940s, he proved that that was unbreakable, provided, and there's some sort of tiny little provisos here. The key is kept secret. The key is the same length as the message. Well, it's quite expensive on key. Key is truly random. Not a lot of truly random things out there. And the key is never reused. So how are we going to get this shared key? Okay. Whoa. Well, one thing you could do is to say, I'll send a messenger with a locked briefcase with the key so that these things shared. And that's exactly how the codes were shared, for example, between Washington and Moscow during the Cold War. Okay. So let's see what we can do. Okay. So let's use it in encryption. So here we've got a legal sender and a legal recipient, Alice and Bob, and a villain who's an eavesdropper. And so what we do is we firstly have unprotected data, which we turn into plain text, just a string of ones and zeros. We fold it in by some sort of transformation. It could be modulo something or other arithmetic, with a crypto key that only Alice and only Bob have. Okay, they transmit the data. Okay, and then the eavesdropper's trying to get a hold of this stuff, but because the eavesdropper doesn't have that key, they can't get any information out of it. Just get a random string of numbers. Okay, so the secret is going to be, how do you share the key? So you could try public keys, and you have these couriers that whiz around with locked briefcases and so on, and you have to trust the courier, and there's no kidnapping, and you have to worry about impersonation. And then Diffie and Hellman started to publish ideas on secure key distribution, but RSA, Rivest, Shamir, Edelman, really came up with the idea that's often used in encryption, and it's the encryption code that one, or a relative of it, that you might want to use using internet security. Actually, much earlier, these characters at GCHQ actually had already worked this stuff out, but of course, because they wanted to use it, never told anybody about it. Okay. And it's using a public key to lock the message and a private key to unlock it. So here's RSA. You've got these safe boxes with two keys. Bob keeps one, the other he sends out to anybody who wants to send him a secret. Then you use the safe box. She's been sent the key, she locks and sends it. It can only be unlocked with a private key, which only Bob has. So, you know, Bob's sitting there with two keys, and then the box is moving there and back, okay? Right. All right, so it's using a trapdoor function, one that's very easy to compute in one way, but really hard in the reverse, and that's this whole business of multiplication and factoring, by the way. And they're related to each other, but it's incredibly hard to derive the private key from the public key. You need lots of calculations. That's that factoring business. Okay. But is it always hard? The largest number that I know of by the start of 2005 had 174 digits. Has he got any better, Arthur? No. Not that he knows, anyway. So, enter Peter Shaw. Classic computer scientist nerd. Sorry, it's what he says himself about himself. And an absolute genius who said, I know how to do this using quantum superpositions. Okay. So quantum cryptography is the whole business. And it started in 1970. Stephen Wiesner, who was the son of the Wiesner who used to run MIT, proposed this idea of quantum conjugate coding, using quantum mechanics in a way that you've got some security, because if you tried to do any interference with it, you modify the quantum system. And he had all sorts of funny ideas. Unforgeable banknotes was one. I think each banknote was the size of a truck in the model. Then in 1984, Charlie Bennett and Gilles Brassard proposed methods using this Wiesner idea, using photons, using light. And 1990, Arthur, who's sitting there, who was coming towards the end of his DPhil in Oxford, under my supervision, I don't know why he had some free time on his hand, but he certainly did have free time on his hand, and was deeply interested in this whole idea of these spooky entanglement things. Came up with a completely new secure communication method based on entanglement. And at that point, physics entered into this scene rather than computer scientists alone, and by working together in a marriage of computer scientists' ideas and physics ideas, there was an explosion of efforts. Lots of groups here got involved. In the UK, a great deal of lead in cryptography by Paul Townsend, who was then at BT Labs, John Rarity, who was at Malvern, and groups in Los Alamos, Geneva, and lots of other places. And they're even trialing these things in financial districts now. So here's the Bennett-Brassard protocol in brief. Here's Alice again, here's Bob. Okay, you have a quantum channel, and you have a public discussion. Okay, and what you're going to do is encode the message. Well, one way of viewing it is you can encode it using polarization. And I could use linear polarizations in various sort of directions. And you send the message in little weak pulses of light, so on average there's 1 photon or less per pulse. Okay, And Bob has a polarization analysis, and you look for unmodified signals. If an eavesdropper is illegally in the way, the act of measurement, in this Bohr sense, disturbs what's going on in the system, and the eavesdropper is revealed. Okay. So imagine, for reasons that escape me, you want to encrypt the words quantum optics. So the first thing you do is you write it in numerical form. Okay, that's easy enough. So C is 3, for example. That's dead easy. And there's a random string of numbers, which is this key we've got to get from somewhere. Okay, I'll come to that in a minute. Okay, and then what you do is you fold them in with an algorithm. And the algorithm here is addition. 19 and 1 is 20. 3 and 20 is 23. Okay, and 20 and 21 is clearly 11. I didn't tell you what basis of it, what modular basis I was using. Okay? It's just addition. Funny addition, but addition. Okay, so we've got the key. That's that string of numbers that only the legal user and recipient, sender and recipient knows. Plain text. And then what happens is, because the recipient has got the key, can unlock it. So what we've got to do is to establish a common random key, string of random numbers that Alice has got, Bob's got, and no one else has, using these funny ideas of quantum mechanics. So we'd like to establish that key. So what we can do is use photons, one at a time. And photons can come in, for example, this is a simplified way of viewing it. Two different linear polarizations. You go linearly polarized that way or that way. Or you could think circular polarization, that way or that way. So there are 4 potential ways of using that photon up. Okay, right, so you could represent a 0 and a 1 by these 2 linears. Or you could use those 2 circulars to represent 0s and 1s. Fine, not a problem. Okay, so here we go. This is what we're going to try to encrypt. Okay, and we use circular, linear, circular, 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 linear. Right. So we send them off. Okay, so here's what Alice sends, here's what Bob's got. And every now and again, it doesn't work. Bob says, actually, I didn't get anything that time. I didn't get anything that time either. That could be because the eavesdropper's got it, or it just got lost. It got absorbed somewhere. Okay? Now, Alice has chosen this set of polarization. Circular, linear, linear, circular, linear, and so on. Okay. Bob doesn't know the basis. Doesn't know whether you use circular or linear. Makes a guess. Sometimes Bob gets it right. Sometimes Bob gets it wrong. Okay? So Bob makes a guess. Linear. Bad news, it was actually circular. Linear. Great news, it was actually linear. Yeah? Just makes a guess. The eavesdropper could be doing the same guessing, by the way. Right. But then, after all the detection's done, Bob and Alice compare bases and says, I sent you a linear. Nothing an eavesdropper can do about it now because they're all gone. And Alice says, I sent you a linear. And Bob says, didn't get one, so I discard it. I sent you a circular. Oh, did get one. Keep it. You don't say which circular, left or right. You just say circular in their public channel. And then you've got this string of numbers at the end where only Bob and Alice knows about. Okay, and you discard all the errors, the ones where you made the wrong guess or whatever. And you've got this string now. Right. Well, this would all be defeated if I could build a Xerox machine that Xeroxed quanta. If I could copy quanta. Now, I can, actually. If I give you a spin up, I can make you another spin up. If I give you a spin down, I can make you another spin down. If I give you a superposition of spin ups and spin downs, and I've only got one measurement, because I've only got one thing, I can't acquire the 2 bits of information I need to do anything about it. So superpositions cannot be copied. So this is good friends, my good friends at HP were probably quite pleased that if I took a wave function and I tried to copy it, that's forbidden. There's no quantum Xerox machines for arbitrary quantum states. Now, back to entanglement. Tariq Ali sent me this website, which I find quite amazing. there's a chap who will sell you art. Okay, this one's for Sandra, and it comes in a nice frame, and it's an equation. Okay, I'm not sure how much you would charge for such an equation, but that's an entangled state of states of zeros and ones. And I did think about ordering one for my friend Arthur. I'm not sure he'd appreciate it yet. But there you go. Even in art, you can buy entangled states. So I did say that Arthur invented this thing, and I want to spend a little bit of time on that protocol. If you take one of these funny entangled states of Schrödinger's, what you can do is you can make these funny things where one of the particles, one of the photons, for example, is in state 0, the other one is in state 1, or the other way around, in superposition. And the funny things about these states, especially that one, which is a singlet, is that it's invariant under rotations, and you can get anti-correlations in all bases. They're so tightly correlated, no matter which way around you try and do a measurement, you'll get a correlation. Okay. So quantum physics can deliver what's sometimes called correlations with promises. At two separate locations, it can deliver you strictly correlated strings. That's exactly what we want in cryptography. So never mind about the Bennett-Brassard one. This has the ability to produce random bit strings that Alice and Bob share and nobody else does. Okay. And these are guaranteed by the laws of nature. So what you have is you have a source, and now you've got to build a source that emits pairs of photons. One Alice got, one Bob got. Okay, you distribute them. Okay, and it provides a way of getting this random key. So Anton Zeilinger, who gave this lecture 3 years ago, 4 years ago? 4 years ago, perhaps. Ruth is remembering. Here is Anton. Pioneered the way in which you can use nonlinear optics to generate these funny, you've got an ultraviolet laser pulse comes in, a crystal, cones of highly correlated light. Where these cones overlap, you get one of these entangled states. And this funny nonlinear crystal, you might wonder why I'm walking around with two laser pointers. That's a red one. Okay, this one is a Russian laser pointer, a green one, which works in the opposite way to this. You take a UV photon in here, and you come out in down-converted to make two reds. Okay? This one is taking two red ones inside and gluing them together to make the green one. So it's like this thing run backwards. Okay? Right. So we can make these things at will. So here's a lovely picture from Anton. He took one of the earliest figures of the human form he could find, the Venus of Willendorf, and he took a key. This is just a bitmap key, and he did an XOR. He just folded it in, and that's my encrypted image. Looks like tartan, but it's actually a completely random bit string. Transmits it, and because Bob has the same bitmap key, he can then decipher this quite securely. Right. And using the Eckert protocol, lots of lovely things have been developed experimentally. So here's a free space one. Okay. Or no, sorry, this is a fiber one. Okay, so here's the river Danube. Here's Vienna. Here's not Vienna. Can't remember what it's called on the other side. Okay, and then there's a classical communication channel, just an RF feed. And then down here, down in the sewers underneath Vienna, they run this fiber link. And that's why it was called the third man experiment. Those of you who remember the Harry Lime movie of people popping in and out of manholes in Vienna sewers, that was what was going on in this experiment. I think it was a loathsome thing to do to graduate students. And they managed to get this key distribution across the Danube. Every now and again, they have to worry about ships coming down the canal and so on, but it was a successful experiment. Or you can do a free space one. Here's a mountain version of it between the Zugspitze, where Alice was sitting, and I can't even pronounce that one, but you can see it. It's another mountain top over there. Free space between them. This was really an excuse for the whole team who pioneered these things to go skiing, I reckon. And they managed to get key distribution across that over a fair bit. This P Knight, by the way, I'd love to say it was me, but unusually, I think it's an appalling career choice, there's another P Knight who actually is a real experimentalist, and it ain't me. Okay, so you can do it on free. Now, if you can do it in free space, who cares about sending it across between mountain tops. But there are satellites up there that need rekeying all the time. Now you think, well, satellites are much further than this, but they're not really, because most of the atmosphere is down here, not up there. So if you can get it across the mountain, you can get it up to the satellite and do rekeying. Right. I have a very good friend and collaborator, Vladimir Buzek, in Bratislava, who's one of the pioneers of a lot of quantum information. He's a theorist. Anton Zeilinger in Vienna. They're separated by not very much. And when Slovakia joined the European Union, they thought it would be good fun to have a message sent by quantum cryptography across the border between Austria and Slovakia. And the Prime Minister of Slovakia was on one side, and various dignitaries from Austria on the other side, and Anton Zeilinger doing the key. And I'm assured by very reliable witnesses that the encrypted message that went from Austria to Bratislava said, "Welcome back to the Austro-Hungarian Empire." And the diplomats were unamused. Anton denies it, by the way, but... Okay, so we're getting to the end. What I've hoped I've shown you is that there's some extremely puzzling features about quantum physics which used to be party tricks. They were things that we would do, and it was sort of physicist party gossip. There were puzzles, things we used to have to really worry about deeply. But this whole business of entanglement is actually making the transition from our party gossip to the workplace. I mentioned much earlier when I showed the idea of quantum jumps that what one can do with quantum jumps is to measure what state of an atom or an ion you're in. And this is the way that we need to be able to do to address single particles, the ichthyosauri in the zoo, raising this particle from the dead. Okay, now if we can do that, that's the basis of the measurement technique by which we can interrogate what state you're in of a single particle at rest. And that would very much be the ultimate in our new generation of atomic clocks. And so the experiments, for example, done by Patrick Gill are really promising in generating exactly that for us as our next generation to replace the cesium beam standards that we have at the present time. But better than that, we can use it for a number of other possibilities, the things I haven't mentioned. There's a thing called ghost imaging that I was tempted to tell you about and didn't. The encryption side of it is already making this transition. So these boxes over here are boxes manufactured by companies who are out there selling them to people who really need this guarantee of quantum, as I said, trust us, I'm a quantum physicist. Okay, so you can buy these things from ID Quantique or from Magic Q, and inside these boxes they will give you an encryption which is becoming comparable to the sort of things that would cost you if you were using RSA. But now you have quantum mechanical security. And so these are really not the sort of thing you would use in everyday life, but would use for high-cost transactions, like moving financial information around. And already that's being trialled in the City of London, and a group of experimenters in Cambridge have been working on ways in which that would actually be generated. In Singapore, where Arthur's other half of his team are, again, people have been testing this in terms of sending financial information. And bank transfer information has also been sent around in Vienna. Okay. People take this very seriously. There's a roadmap here that's looked after by Los Alamos. It's not as sophisticated as the semiconductor roadmap, but it is something which people really take seriously. Now, I've been telling you some of the things that we just have lots of fun on these things, that we've got large-scale collaborations involving our partners in Europe. But it also involves a team, and people get lured into these teams where they, I don't know whether they trust my vision or not, but they certainly are willing participants in a major adventure. I don't know why the Berlin police force have such a stunt. It is. He looks very unamused if you turn upside down. But none of this is done on my own. I'd like to thank a vast team of people. What I've done is written down the senior people, the permanent people, the people that have really enabled us to enjoy what we're doing at Imperial. Martin Plenio, I think most of these in the audience, Elmer Beiger, Anne Curtis, who's here in the audience working with Ed Heinz Group, Jens Eisert, Ed himself, Terry Rudolph, who's here, Stefan Scheel, Danny Siegel, who coordinates a major network called Q-Gates, and Danny's been struggling today to get the final report into Brussels on that one. Richard Thompson, he and I have been working on these things for a long, long time on this. Lots and lots of students and postdocs, a lot of them in the audience I see, but I'd like to especially to thank Arthur, because without Arthur I would have stuck at doing quantum optics, and it was with his enthusiasm for this field and his insights that dragged me into it. At HP Labs, we've got a very close collaboration with HP, with joint students, and it's really a pleasure to welcome Tim Spiller here. Bill Monroe is a visiting lecturer in our group. He's actually still in Australia, where he's doing some collaborative work. At National Physical Laboratory, Patrick Gill, who I know is in the audience, JP Jansen, Alistair, I was meant to say Sinclair, and lots of other people, not only are doing the trapped ion work, but are beginning to worry about provable security. I said, trust me, I'm a quantum physicist. But sooner or later, DTI, the paymasters of NPL, will say, how reliable is this stuff? What are the standards for it? Give us some reproducible standards that we can actually see. And that's one of our major tasks in the coming year or so, to begin discussions with the National Measurement System labs around the world to agree on how we'd approach this very interesting variant of this kind of thing. Thank you very much for listening.
Well, it's my great honor and pleasure to be here and to give this vote of thanks, to thank Peter for his wonderful lecture. But I have to admit that I really do not know how to give a vote of thanks. The whole concept is not entirely well defined as far as I'm concerned. So before I came here, I had this brief communication with Peter, and I said, well, look, I think that's a little bit like being a best man at the wedding, where you have to crack in a few jokes, mildly insulting, and say a few good things about the speaker. But then Peter said, well, no jokes, you know, you have to be serious and proper. There will be quite a few Austrians in the audience, so you have to make sure that it's so, okay, I thought, well, I'll forget about those embarrassing pictures that I have in my album with Peter, and I will not show them here, and I'll just can assure you that Peter is a very serious, very shy, very quiet person, and those who know him know he never lost temper with anyone. I owe Peter a lot, I have to say, and it's not only me. Quite a few people now here in Britain, in Europe, in the United States, in Australia, in parts of Asia, that worked with Peter, or had a chance at least to discuss physics with Peter. And what I really admired about Peter is his enthusiasm, that he can convey in really simple terms so much and make you enthusiastic about it. So Peter says that, you know, that I played a role to take him away from quantum optics. It's not true. I never took him away from quantum optics. And I think he perhaps doesn't realize that it was actually his enthusiasm that encouraged me, and his encouragement that made me actually to wonder and to look for interesting and fascinating topics. And another thing that I should say that I owe Peter a lot is his simple advice when it comes to scientific method. And I thought, you know, I know something about scientific methods. I read Popper and thought about conjectures and refutations. I I read Kuhn and was interested in the notion of paradigm. But actually, the real scientific method that I learned from Peter was when one late evening we were here sitting at Imperial College. I was visiting from Oxford and staying quite late because there was probably some kind of a problem that we wanted to crack. And I was sitting in front of this blackboard in his office trying to understand and solve something, and Peter was away, and then he came and both of us actually looked at this blackboard for another 15 minutes and nothing came out of that. And Peter said, you know, let's have a couple of pints. Things will be much more clear after that. And you know, it worked. And I knew that we'll have many years of working together since. So Peter, thank you very much for all your scientific, non-scientific and semi-philosophical contribution that you've made. And I think I should say on behalf of many people who worked with you and who had a chance to interact with you, how grateful we are for your encouragement to explore physics and as you said, always to encourage us to explore what we are really interested in. Thank you very much.
You've been listening to a special lecture vodcast from Imperial College London.